I'm pleased to introduce the last speaker of today's session, Professor Giles. Professor Giles is a professor of scientific computing at Oxford University since 2008. His research concerns high-performance computing, and his signature work is on multi-level Monte Carlo methods. He completed his PhD in 1985 at MIT and went on to become a faculty member before moving to Oxford. Please join me in welcoming Professor Giles. Professor Giles.
Thank you very much, Eitan. So today I'd like to talk to you about multi-level Monte Carlo methods. And the key things I would like to get over in this talk, the first is that it's such a simple idea. And it's more of an approach that can be applied to a wide variety of applications. But each new application class that you come to, there's some creativity possibly involved in thinking through how to apply that. And so I'll cover a number of different application classes. And also, there's a huge number of people working on various developments of this in these different application areas. So I'll be mentioning names as I go by. And right at the end, I have links to a web page that I maintain that sort of lists what all the various groups working in multi-level are doing, and lists all of their research papers. So you can follow up the details of those if you'd like to afterwards. So very much focusing on ideas rather than showing you lots of results. OK, so we're looking in the context here of stochastic simulation and uncertainty quantification. And so in stochastic models, we have some input randomness, I represent as omega. And then typically, we have to solve some intermediate problem, generating these variables S. And then having done that calculation, then there's a single output quantity of interest P. And here, I'm going to start by assuming that that's a scalar output quantity. And then what we're interested in trying to estimate is the expected value of that output quantity P. And the Monte Carlo method is such a trivial method that we simply take n independent samples omega, and for each one of those, we perform the calculation, we compute the output quantity of interest, and then we just take a simple average of those. So that's, as it stands there, an unbiased estimate. So the expected value of the Monte Carlo average y is equal to the true expected value of p. And then with the central limit theorem, as long as the variance of p is finite, then the error, as we increase the number of samples, the error is normally distributed, and the variance is 1 over n times the variance of a single sample of p. Okay, so that's what gives us our classic 1 over square root of n convergence for the root mean square error. So if we want to achieve a root mean square accuracy of epsilon, that means that we're going to need order epsilon to the -2 samples. So potentially, we're looking at very large numbers of Monte Carlo samples. And that's why, although Monte Carlo has been used a lot historically for areas like stochastic differential equations, when we get into stochastic PDEs, in the past it's been viewed as being prohibitively expensive. And this is what multi-level is really sort of addressing, is trying to improve that. Now here, we were able to exactly calculate the intermediate variables S, and therefore the scalar output P. But in many cases, it's not possible to perform that calculation exactly, particularly when we're solving an SDE or stochastic PDE. Then we have an approximation being involved in there, coming from a discretization. And so instead, we're generating these approximate intermediate variables S hat, and from those deriving an approximate output quantity of interest P hat. The Monte Carlo estimate is, again, just an average of n independent outputs, But now the mean square error has a decomposition into a term as before, which is 1 over the number of samples times the variance of p hat. But now we have this additional term, which is the square of what's known as the weak error. It's the discretization error in expectation. Okay. And so achieving greater accuracy for the mean square error requires not only increasing the number of samples n, but also making the calculations more accurate so that the expected value of p hat is closer to the true expected value of p. Now, when I started this work, I was interested in applications in computational finance. And so we were interested in solving stochastic differential equations. So this is our generic form of stochastic differential equation. We have a drift term, a deterministic term, and then this is the stochastic term with a diffusion coefficient b, and then dw is the increment of a Brownian motion. So over a small time interval dt, this increment dw is normally distributed, and the variance is equal to dt. And so this is typically approximated by the simple Euler-Maruyama method. It just corresponds to standard forward Euler time integration for doing ordinary differential equations, where we freeze the drift and diffusion terms at the beginning of the time step, treat them as constant, and so integrating over the time step, we just get the drift times the time step h, and I'm assuming here a uniform time step h. And then for the diffusion term, we have the initial diffusion at the beginning of the time step times the change in the Brownian path over that time step. Okay. And then in simple finance applications, the quantity of interest is some function of the terminal value of this path S at a final time capital T. There are more general financial models or financial outputs of interest which depend on the entire path, but we'll just keep it simple for the time being. So this is just a simulation of a couple of paths approximating with, well, we're solving geometric Brownian motion. This is a classic SDE underlying the Black-Scholes financial model. And I've got two simulations here which are for the same underlying Brownian path, but a coarse path with large time steps, just 4 of them, a fine path, twice as many time steps. And the key thing is, there's a lot of variation during each of the time steps, but overall, there's not a huge difference in the path values at the final time. Okay. Now, when you have that kind of discretization, the Euler-Maruyama discretization, there are 2 kinds of discretization error associated with that. One is the weak error, which I've already mentioned. It's the error in expectation between the expected value of the approximate output p hat relative to the expected value of the true output p. And it turns out that for the Euler-Maruyama method, that's asymptotically proportional to the size of the time step h. There's also the strong error, which is the root mean square error, or the root mean square of the sup error between the path simulation, S hat, and the true path, ST. Now, we have to define an appropriate interpolant of this between the various time steps, but given a suitable interpolant, then this root mean square difference between the approximate path and the true path, that scales like the square root of the time step. This is really a pitiful order of convergence. For anyone who's used to ordinary differential equations where you'd typically be doing a 4th order, 5th order Runge-Kutta, to have something that's only half-order convergent, it really isn't very significant, isn't very good. In fact, once you do multidimensional SDEs, it is actually extremely difficult to do better than this. And so in fact, if all you have is information about the Brownian increments, uniform time steps, that is the best in general that can be achieved. But for scalar SDEs and for certain classes of multidimensional SDEs, there's another more sophisticated discretization, the Milstein discretization, for which both of these errors are of order h. And that's in practice the one that I prefer to use wherever possible. Okay, so let's look at that mean square error term that I talked about before. The variance term scales like 1 over the number of path calculations we perform. The weak error I said was proportional to the time step, and so the square of that, we get an h squared here. So if we want to achieve a root mean square accuracy of epsilon, then we need the mean square error to be epsilon squared. So it says that the number of path simulations has to scale like epsilon to the -2, as before, as we had in the unbiased case. But the size of the time step has to scale proportional to epsilon. And then the total computational cost will be the number of paths times the number of time steps per path. So the total computational cost is of order epsilon to the -3. Okay. And I want to make that better. So what can we do to reduce the overall computational cost? Well, we have to tackle one or other of these two. So to reduce n, the number of independent samples that we take, there's a lot of classic techniques in variance reduction which leave it still as being epsilon to the -2, but they reduce the multiplicative constant out front. Or we can use quasi Monte Carlo methods. So rather than sort of truly random numbers being generated, they're being constructed in a very systematic way that provides a more uniform coverage of the probability space. And the consequence of that is that this exponent 2 can be reduced. And in the best case, you get close to epsilon to the -1. Okay, so those are classic methods in the Monte Carlo literature. But what we're going to do here with multi-level is really tackle much more this piece. That what we want to do is reduce on average the cost of each of our simulations. So how are we going to do that? Well, this is the key slide. And it really is an incredibly simple idea. Suppose there's some quantity we want to estimate the expected value of. So expected value of p hat 1. But there's some other quantity p hat 0, which is much cheaper to simulate than p hat 1. And yet p hat 0 is close to p1. Okay? Then we have this trivial identity, that the expected value of p hat 1 is the expected value of p hat 0 plus the expected difference. And rather than directly estimating the quantity on the left-hand side, we're going to independently estimate each of the two quantities on the right-hand side. So we can estimate this one, standard Monte Carlo estimate, using n0 samples. And then this one, we're also going to estimate using a standard Monte Carlo estimate, but with a different number of samples, n1. Okay. Now, the point here is that this n0 is going to be roughly the same number of samples that we would have used if we had directly tried to estimate this expected value. But each of the p0 calculations is cheap compared to calculating p hat 1. So the cost of that calculation there is much less than the corresponding calculation would have been for p hat 1. And then this term here, because p hat 0 is close to p hat 1 in some sense, then the variance of that difference will also be a small value. And because the variance is small, we need relatively few samples N1 in order to accurately estimate the expected value. And that's where the savings is coming from. We're going to do relatively few accurate calculations, the p hat 1s. We'll do lots of p hat 0s, but they're nice and cheap. And therefore, overall, we save very substantially. Now, as soon as you have a two-level approach like this, and particularly for somebody like me that had a background in using multigrid methods in CFD calculations, it's very natural to go to a generalization with a whole sequence of levels. So all the way from p hat 0 to p hat capital L. So p hat capital L is going to be the finest level of resolution, and that's the one where we really want to get the expected value. And so we have this decomposition as the expected value of p hat 0 plus this telescoping sum of corrections. And each of these corrections will be independently estimated. So we have this estimate for the first term, and then a sum of estimates for the expected correction on each level. Okay. So if we now define C and V to be the corresponding cost and variance of these quantities, so on level 0, we just have p hat 0. On the higher levels, we have the difference of level L minus 1. Then the total cost is just going to be a sum over level of number of samples times the cost per sample. And the overall variance, because we're doing independent estimation on each level, the variance of the sum over the levels is just the sum of the variance on each individual level. And on each level, the variance is the variance of a single sample divided by the number of samples. So then we want to do a constrained optimization. We want to minimize the total cost to achieve a fixed variance. And so treating the NLs as being real numbers rather than the integers that they really are, we introduce a Lagrange multiplier to constrain the variance. We differentiate with respect to NL, and that gives us the optimally NL should be proportional to the square root of the variance of a single sample on level L divided by the corresponding computational cost. Okay. And the way these levels are organized, as we go to finer and finer levels, the differences are going to be smaller and smaller, and so the variance will be getting smaller and smaller. And at the same time, the accuracy comes at a price. So the computational cost of the simulations is going to be increasing with level. And so for both of those reasons, this ratio V over C will be tending to 0 as the level L increases. More interesting in some ways is actually the product, NL times CL, because that product represents what's the share of the computational effort that's being expended on level L. And that product then is proportional to the square root of the product of V times C. And here it's less obvious what the trend will be as L tends to infinity, or as L progressively increases. Because the variance is coming down, the cost is increasing, which of those two is going to win out? And that depends very much on an application. So in different cases, different ones will win out. So if we now set the fact that we want the total variance to be equal to epsilon to the minus 2, then that gives us the value of the Lagrange multiplier mu, and hence we get this expression for the total cost. If I then correct for the fact that the number of samples is actually an integer, so I round up to the nearest integer, then there's a small extra term that comes in here, but it's negligible in almost all circumstances. And so this is really the dominant term in the cost. And that total cost can be compared to standard Monte Carlo, where we'd again have order epsilon to the minus 2 samples, and then we would have the variance on the finest level. Well, typically the variance on each of the levels of just the quantity p on its own, not the difference, it doesn't tend to vary a huge amount. And so roughly that will be the variance on the coarsest level. But because we're doing the simulation on the finest level, the cost will be CL. So that's the cost of the standard Monte Carlo approximately. This is the cost of the multi-level. And so you can look at what the ratio is between the two. And the expression for the savings depends on whether this product is increasing with level or decreasing with level. But either way, you win out. You either win out because the variance of the difference on the finest level is much smaller than the variance itself on the finest level, which is roughly on the coarsest level, or you win out because the cost on the coarsest level is much less than the cost on the finest level. So let's go back to the SDE example I was interested in. So if I'm doing, on level L, I'm using capital M to the L time steps. Typically, I'll go in powers of 2 or maybe 4 on the different levels. Then the cost will be inversely proportional to the size of the time step h. My estimator then, I'm wanting the expected value of the difference between the simulation on level L and simulation level L minus 1. And the key thing is that, I want these to be close to each other, and that comes from using the same Brownian motion to drive both of those simulations. What does that mean in practice? It means that for the finer of the two simulations, I generate my Brownian increments, delta W, for each one of the time steps. And then if I'm going in powers of 2 with the time steps, I just sum them up pairwise to get the corresponding Brownian increments for the coarse simulation. Okay, so it's a very simple, natural thing to implement. Okay. So then the analysis of the mean square error, we again get a decomposition into the variance plus the square of the weak error. The square of the weak error, well, that's all to do with the error on the finest level of approximation. Whereas the variance term is the sum of the variance contributions from all of the different levels. Okay. And so to make the root mean square error less than epsilon, we choose the number of samples on level L to be proportional to the square root of the variance over the cost, and the constant of proportionality is chosen so that the total variance is less than 1/2 epsilon squared. And then the finest level of resolution is chosen so that this error term here is also less than 1/2 epsilon squared. And so then the sum of the two is less than epsilon squared. Okay. So in the simple case of an output function p, which is a Lipschitz function of the final value of the underlying path s, then the variance of the difference is less than the expected square of the difference. And because of the Lipschitz property, then that's less than the Lipschitz constant squared times the expected square of the difference between the fine path approximation and the coarse path approximation. But in the Euler-Maruyama case, each of those in root mean square is within order square root of h of the true path, and so the difference is also of order square root of h in the root mean square sense. And if we don't take the square root, because we don't have that here, then that means that that's of order h for the Euler-Maruyama. For the Milstein, because it's got better strong convergence properties, then this becomes order h squared. So if we look at the product of variance times cost, I said the cost was inversely proportional to h. So in the Euler-Maruyama case, that's of order 1. In the Milstein case, that's of order h. What does that mean? That means that in the Euler-Maruyama case, we have roughly equal spread of computational effort on all the different levels of resolution. We have lots of cheap calculations on level 0, very few expensive calculations on the finest level, but roughly an equal balance across all the levels in terms of computational cost. Whereas in the Milstein case, this product decreases with level, and so the dominant cost is actually on the coarsest level of resolution. Very little effort expended on the finest level. So we then come to this theorem, which sometimes I call a meta-theorem. If I'm feeling more honest, I describe it as a bit of a cheat, this theorem. And it's a cheat in the sense that I assume lots of lovely properties. And then I say, if I have all those lovely properties, what's the consequence? And actually, the hard work in real applications is to prove that those lovely properties actually hold. Okay? So what do I want? Well, I'm assuming that I have these levels. I'm assuming that the weak error decays exponentially with level at a rate controlled by alpha. I assume that I have my estimator y hat on level L, which has an expected value that does the right thing, so that the telescoping sum works correctly. I assume that the variance, well, the variance will automatically go like 1 over n, but I'm assuming here it also decays exponentially with level at a rate controlled by beta, and I assume the cost goes up exponentially with level at a rate controlled by gamma. Usually, getting gamma is relatively obvious. Alpha, usually there's a lot of literature that tells you about the weak convergence order. It's the variance one that tends to be the difficult one in doing applications, to work out this rate beta. Okay. But if you have all of those features, then we can do the multi-level calculation. We can optimally choose the number of samples on the different levels such that we achieve the epsilon squared mean square accuracy with a total computational cost that scales like this. So the good case is when beta is greater than gamma, because when beta is greater than gamma, the rate at which the variance comes down is faster than the rate at which the cost goes up. Okay. And so that's the case where the dominant cost is on the coarsest level, and we get overall an epsilon to the minus 2 complexity. In the case where beta is equal to gamma, this corresponds to the Euler-Maruyama case. And in that case, we have an equal spread of effort across the levels, and we end up with this cost going like epsilon to the minus 2 times the square of log epsilon. Essentially, this term here is capital L squared. It's the square of the number of levels involved in the simulation. And then the case that I try to avoid wherever possible is beta less than gamma, in which case we get this more complicated expression. It's still better than regular Monte Carlo, but it doesn't quite get to the epsilon to the minus 2 complexity, which I always strive for. Okay, so 2 comments on this. On my very first slide, I said that Monte Carlo simulation, in the case where you can exactly simulate the quantity of interest, we need epsilon to the minus 2, or order epsilon to the minus 2 samples. And so in that case, when beta is greater than gamma, we're basically getting a suboptimal Monte Carlo behavior. We have a cost that's order 1 per sample on average. Okay. To do better than that, we'd have to introduce the quasi Monte Carlo ideas, and that can be done, has been done, and that does further reduce the cost. Another interesting case when beta is less than gamma is that in a number of applications we have beta equals 2 alpha. And when beta equals 2 alpha, this beta over alpha here cancels the 2, and so we end up with the cost being of order epsilon to the minus gamma over alpha, and that corresponds to the cost of a single calculation on the finest level of resolution. And so again, you can't do better than that. Okay. There's a generalization of this to handle cases where the output P is not scalar, where it's actually multidimensional or even infinite dimensional. And that links into some original work by Stefan Heinrich in 1909, where he was looking at this in the context of parametric integration, so this problem here. In his case, he was interested in a finite dimensional random variable. So he had finite dimensional random inputs and infinite dimensional output. In the SDE case, I was interested in an infinite dimensional random input, a finite dimensional output. There's been a whole lot of work on different aspects of this with SDEs. There isn't time to go through all of these. Also looking at Levy processes in addition to standard Brownian diffusions. This is just to give you a sense of the variety of applications that people have been working on. The extension is also very natural to stochastic PDEs, or PDEs with random data. And again, a large number of people working on different applications, parabolic, elliptic. This is one of the classic applications, is an elliptic problem in which the diffusion coefficient is actually a stochastic field. So it's, the log of the kappa is a Gaussian field. So at each point in space, it's normally distributed, and then there's a spatial covariant structure to it. So Christoph Schwab's one of the key people in doing applications of stochastic PDEs, and he and his group have investigated a whole range of different PDE models. Just as a simple example, consider the case of a 3D elliptic PDE where we've got random boundary data. Okay? And so again, if we have grid spacing proportional to 2 to the minus L on level L, so we're doubling the resolution on each level, if we have a really good multigrid solver, the cost will be proportional to the total number of grid points. So that'll scale like 2 to the 3 alpha. So that gives us a gamma of 3. If we have a second order accurate numerical method, then our output quantity of interest will have an error that scales like 2 to the minus 2L. And so that will apply both to the level L error and also to the difference between level L and L minus 1, scale like 2 to the minus 2L. So that gives us an alpha of 2, and then we have to square that for the variance, so it'll give us a beta of 4. So this is, again, just illustrating how you get these parameters, alpha, beta, gamma, for a simple new application. And then you just plug those into the theory, and that tells us that we're in the regime beta greater than gamma, so we're going to get the optimal epsilon to the minus 2 complexity, and you can compare that to what would be the cost of a single sample on the finest level. And then if we did epsilon to the minus 2 of those for the standard Monte Carlo, then that's what the cost would be for standard Monte Carlo. I would say about 95% of the literature now on multi-level Monte Carlo has a geometric sequence of levels. That's a sort of natural thing in many, many applications. But it is not a requirement of the multi-level. I just want to make that point, that all we really need is a sequence of levels with increasing accuracy, but at increasing cost. We have that trade-off. And so increasingly small differences between the output quantity of interest on successive levels. And just as an example of this, those that work at MIT using multi-level in the context of reduced basis approximations, where they had an extremely fine finite element discretization, and then they solved it for a few values of the stochastic parameter omega, And so that gave them a few solutions UK. And then they said, OK, let's use that as a reduced basis so that for other values of omega, we'll decompose the solution U as being some linear combination of that reduced basis set. And that leads to a low-dimensional reduced system to solve. Now here, depending on the size of the basis set, using more basis functions will give you greater accuracy, but there's going to be greater cost. So again, it's the natural multi-level setup. And so they did a multi-level treatment in which the number of basis elements, they varied with level. And they actually did a brute force optimization to work out the optimal number of levels, and then from that you get the optimal number of samples on each level. An application I'm very interested in currently, driven by interests in financial risk estimation, is nested simulation, where we're interested in the expected value of a quantity G, which is itself a function of a conditional expectation. So the outer expectation is with respect to this random variable x, and then the inner expectation is with respect to the random variable y, holding x fixed. So where does multi-level come into this? Well, if we assume that each of those inner samples, little f, can be evaluated with unit cost, what we're going to do in the multi-level is to vary how many inner samples we use to approximate this conditional expectation. So we're going to use 2 to the L inner samples on level L. So how do we set up the coupling? And this is a case where it's quite a different coupling strategy to the Brownian one, where it was very natural. And this gives an idea of the sort of flexibility of the approach. So what we're going to do here is on level L-1, we want to use 2 to the L-1 independent samples. And I'm going to use this antithetic estimator. So first, I generate one set of 2 to the L-1 samples of y, and I use that to get this f bar A. And then I use a second independent set of 2 to the L-1 samples to get the f bar B. And then I put those two sets together, and that gives me a combined set of 2 to the L samples, and that's what I use for this f bar. So that's the one I'm using for the fine level. And why is this a good combination? Well, the overall average f bar is the average of the two independent coarse approximations, f bar A and f bar B. And so with a bit of rearranging, I get this. And so relative to f bar, the f bar A has this error, the f bar B has the negative error. And that's why I refer to this as an antithetic sampling, because of the idea of plus and negative errors that are going to cancel out to a large extent. Because then we do a Taylor series expansion for G, expanding around f bar. And when you do the Taylor series expansion, the linear error terms here are going to cancel out. And what you get is this quadratic term. And because of the averaging here, the averaging will differ from the true expected value by something proportional to the square root of the number of samples. But when I square that, then that's going to give us an error that's behaving like 2 to the minus L. So what are we going to get? So that's going to give us an alpha of 1. And then the square of this is what's going to give us the variance. So that'll give us a beta of 2. And then the gamma is again 1, because the cost scale is like 2 to the L. So again, we end up in this great regime where beta is greater than gamma, and so we get the optimal complexity. So there was some work on this done by a Abdul Latif Haji Ali, who was working at KAUST. He's now working in Oxford as a research fellow. And there was also some work by colleagues in Oxford doing a credit modeling application. In their case, it wasn't twice differentiable. It was continuous and piecewise differentiable. And so in their case, it had a beta of 3/2. Another example of the flexibility of this is applications where we can think of performing the calculation with different precision levels on computer hardware. So there was work at TU Kaiserslautern where they were using field programmable gate arrays where you can control how many bits are used to perform the calculations. And so they increased the number of bits of precision on the different levels. I've got a student who's starting work on GPUs in which, as well as having single precision and double precision, there's also half precision, half floating point precision, 16-bit floats. And so again, multi-level can be used so that you can get full double precision accuracy, but doing most of the calculations at half precision. Or you can use different random number generators. So Oliver's looking at using level 0 with a 10-bit uniform random number generator. And with 10 bits, that's 2 to the 10 possibilities. You can just use a lookup table to convert those to approximate normal random variables. Whereas on level 1, you can use a 32-bit uniform random number generator and then properly invert the normal CDF function to generate normals. Okay? There's just all sorts of different ways that you can use this multi-level approach. So here's, again, a list of different application areas that people are working on. So there's work on multi-level Quasi Monte Carlo I mentioned. So I did some work with Ben Waterhouse, originally 2009. But really, it's the papers by Schwab and collaborators where that's the main literature that I would refer people to now. Very interesting work on stochastic chemical reactions. When you get down to really low chemical concentrations, it becomes a stochastic process. You know, what's the probability of molecules bumping into each other and reacting? And so there are huge savings to be achieved because they're interested in applications where there may be tens of thousands of individual reactions to take place. Applications of multi-level to Markov chain Monte Carlo. So that's a whole interesting application class where I really don't understand the details of what they're doing in that area. Likewise, I'm not clear on the details of what's happening down here. So it's being used creatively by all sorts of different people, in each case trying to think how the ideas apply in the setting of their application class. How am I doing? I think I may have to skip these. There are also some interesting extensions of the fundamental ideas of multi-level. So this paper by Rhee and Glynn, what they do is a sort of randomized version. They don't say, we're going to go up to level capital L and never go beyond that. Instead, each individual sample, they randomly determine which level of resolution are they going to use in order to perform the calculation. And so they have to have a probability distribution as to what's the probability they're going to work on level 0, what's the probability they're going to work on level 7. And it relies on the fact that beta is greater than gamma in order to end up with something that has absolutely no bias, but does have finite expected cost and finite variance. And so that's interesting. This work by Lemur and Pdes is particularly helpful when beta is less than gamma. So this is doing a Richardson-Romberg extrapolation in order to reduce the number of levels that have to be simulated. So essentially, it's trying to improve the weak order of convergence, so you don't have to go to quite so fine a level of resolution. And that's very helpful in these cases. And then multi-index is for applications where you maybe have the number of time steps is one parameter, but maybe you're varying in the other direction, something like the computational precision level. And so there are two things that can be varied independently, and so it's a sort of higher dimensional generalization of multi-level, which is also very effective in various cases, and links into the literature on sparse grid methods. Okay, so I'll just skip over the slides I had for that, and just come to the conclusions. So, I hope I've got over to you the key idea of multi-level, and it really is as simple as it hopefully looked. Okay? The interesting in new applications is to figure out how to take the kind of philosophy and apply it in detail to a new application class, and then performing the numerical analysis can often be quite challenging. I haven't talked about the problems with discontinuous output functions. Typically, when you're doing simulations on the fine and coarse path, the S-hat approximations are very close to each other. But if the P-hat output is a discontinuous function of the S-hat, you can have small differences in S-hat giving an order 1 difference in P. And that makes the variance much worse. So we have a whole bag of tricks to address such problems to make it better than it would otherwise be. But it's been used for a huge range of applications. The biggest savings are when the coarsest adequate approximation is much cheaper than the finest level, which is the one that you want the accuracy of. And so people are typically getting savings of 100 or more on PDE applications particularly, and the stochastic chemical reaction networks. That's probably the two classes where people get the biggest savings. Okay, and then I'll just conclude with some web pages where you can get all of the details of my research. I've got an Acta Numerica review article that surveys the field. That's from 2015. And then this is my community web page where I try to keep track of all of the research being performed on multi-level. And so you can see for your application areas of interest who's working on it and what the papers are that are available. So with that, I'll conclude. Thank you.
Questions?
No speak English. Если кто может, я по-английски не говорю, если кто может с русского на английский перевести. No speak English, я потом подойду. No speak English, I speak Russian. Ну, у меня вот много работ по этим. Quasi Monte Carlo, но я потом подойду.
This requires a multi-level solution. Let's conclude here. Let's thank Mike and the other two speakers this afternoon.